have lost my eraser. Okay. So one thing that we're going to cover today is this is exclusively on rectifiers. And this may seem like an odd topic because we haven't really described what rectifiers do or what they are, but that's kind of the point. We're going to mainly do this with diodes, and we're going to start with our half wave. From a previous lecture, this should be fairly self-explanatory or self-descriptive here, but we're going to start with an AC waveform, really anything, and we're going to drop it through a diode, and we're going to drop it through some load, okay? And we're just going to call that V out, okay? And so we already did this a little bit, but I just wanted to point out a few interesting things. What we end up with is, over time, maybe a sine wave that we put in that looks like that, the voltage that we get over the resistor is just going to be half wave rectified, meaning this. And we could put this into all sorts of different formats as far as describing it. And you could say something like, if you have a V in greater than 0, then V out is equal to V in. V in less than equal to 0, V out is equal to 0. That's probably one of the easiest ways. Now, I do want to note that this is for ideal diodes, okay, perfect ideal diodes, okay? So we could describe it with an expression like this. We could describe it with V in and V out here, and what we're going to come up with is a little plot that looks like this. Has a discontinuity right at the origin, and this slope is 1 to 1. So we put in 5 volts, we get out 5 volts. And once again, this is for an ideal diode. I am going to have to find my eraser at this point, because I don't think I can do that. Yep, there we go. Okay, so rectifiers, half wave, that is our half wave rectifier. Okay, we're going to call this one the bridge. Call that P1. Another diode there. A lot of times they will make these bridge rectifiers. And they'll make them in a diamond format, and I think that's a lot harder to understand. And I'm going to do RL plus minus VL. I think it's a lot harder to understand than by doing something like this. And this is our AC V in wave format for this. Now we're going to augment these models in the future to make them more complete. But the thing to understand is when VI is positive, we're going to get current that's going to try to shove this way. And obviously it can't go through that one. It's going to want to go through this diode and that diode, and its current direction is that way. If we have negative voltage, it's going to try to shove current this way, but instead it's going to take this pathway. But if you look, both current pathways are positive through, well, RL as far as what we did. And so if we go and we make our same wave format like that, now that looks pretty good. If we make that same format like that, and we look at what the current is, so for the one blue pathway, it's when it was positive, and it's just going to match because those diodes are ideal. For the red pathway, though, we're going to get an opposite polarity voltage over that resistor. And so it's going to give us this over RL, and so our combined waveform is actually full wave rectified. And so this is kind of an interesting way to describe it, but this is a full wave rectified a full wave rectified signal. Bridge rectifier is what we call this. This is really common. It's very easy. Takes 4 diodes. There are downsides to it, and mainly one of those is it has 4 diodes. But once we get into non-ideal diodes, it'll help us understand that a lot better. We could describe this with that plot that I had before, and where this is V in and this is V out, or V load in this case. It looks just like this, and this should be, I mean, mathematically we can actually describe this pretty easily. V out is equal to, so that's actually kind of mathematically, we've done nonlinearities, and both of this line is a negative 1 to 1, this one is a positive 1 to 1, and so that's what a bridge rectifier does for us. There's one more kind of power rectifiers, and so I'm going to even say at this point that these are power rectifiers. The non-power rectifiers don't make much sense until we actually look at non-ideal diodes. So let's look at the last one, and this is going to be, I'm going to call it full wave rectifier. And the last one, the bridge rectifier, was a full wave rectifier, but to differentiate, we're just going to call it a bridge rectifier. This one is our actual full wave rectifier. And one of the challenges that we have from this one is we're going to start with our same, I'm going to just call this VS this time, rather we can call it VN, just to keep consistent with what we've been doing. But we're going to use, somebody asked me to make sure that I had all of my players. So this is a center tap transformer, and I've just drawn it as two, transformer, and so we'll have 1 to 1 to 1 ratio on each one of these. But this is really just a center tap transformer. You can buy these. What they do is they splice in the middle a winding that comes out, and then these are 1 to 1. In this particular case, this is going to be 1 to 1. So what we'll get here is positive VI and positive VI. Okay, in both of those. And I'll draw polarity signals on there so that we know the difference. And there's some super big advantages to this one. Generally, we use a transformer anyway, and funny enough, when if you took the EELE 101 class, this is what we did, and there were 4 diodes in that circuit, but that's because we did both positive and negative rectification. But this is the transformer circuit that we use. This is going to be our RL. I'm going to do plus minus there. And what happens is when VI is positive, we get current that makes its way like this, but it's blocked by this diode. It can't go this way, and the current also wants to be pulled that way, so no good. On the other half of the rectification, if the VI is negative, and so you see it goes through RL both ways, and we end up with exactly the same math as before, which is our original goes in this way, and we end up with, I'll just do it in blue, we end up with, I'll do the shorthand format of it, but the math is pretty much the same. There are advantages and disadvantages in real life to each one of them, but we end up with full wave rectified signal from that. One of the disadvantages is you definitely need a transformer for this. If you don't need a transformer, this is not the way to go because it adds in a large amount of hardware that you're going to want to avoid having in your circuit. The other thing about this to avoid that happens is these diodes get reverse biased by a large amount of voltage in here. It's going to be double VI if you think about it. And we'll do some more equations on that when we get more, but I wanted to introduce you to the full wave rectifier. And that's it for our 3 power rectifiers. There is something called a signal rectifier, but we have to describe the non-ideal diode first, and so that'll be the next lecture.